my my focus is not going to be so much on the data during most of the presentation until towards the end, where I'll give you some examples of fog data, um, some maybe a drop in the bucket, so to speak, of all of the fog data we've been collecting recently. So first question is, what is fog? This is an important consideration because when I started researching fog, I got it wrong at first too. I made the statement that, oh, fog condenses on plants or whatever, and fog does not condense. It is already condensed. Fog is fine particles of water, as Merriam-Webster states, that are actually floating around. So fog is actually a liquid, tiny little droplets floating in the air. And I don't really love the definition of Merriam-Webster and the fact that they use the word vapor, because while fog is vapor that's condensed, any droplet was probably vapor at some point, but it makes you think that fog is a vapor, and it is not. It is actually a lot of little droplets. There's certainly vapor in the water, but the fog itself is not a vapor. So I would say the definition of fog consists of three pieces. One is that it's these little particles. I'll talk about them in a minute. The other one is that it's a cloud that's in contact with the ground. So that's a very easy one to remember. It's like fog is a cloud, specific type of cloud actually, but one that's in contact with the ground. It's not a cumulus or a cumulonimbus. It's more like a stratus. And it's also, in order to be fog, it's supposed to reduce visibility to 1 kilometer or less. So those are kind of the three criteria. There's droplets within a certain size range, it's a cloud in contact with the earth, and it reduces visibility to less than 1 kilometer. Of course, I got rid of I don't like that vapor, so I crossed it out in my slide here just so that I emphasize that. Now, what about the droplets? I mentioned them a moment ago. The droplets have a size, a diameter, somewhere between 1 and 50 microns. You might ask, what is a micron? A micron is a millionth of a meter. A micrometer is another way, or a micrometer, 1 millionth. And to give you some context, your hair is 100 microns in diameter. So the biggest fog droplets are 50 microns in diameter, which is half the diameter of your hair. So fog droplets can be anywhere from 1 to 50 microns in diameter. And so they're all smaller than the diameter of your hair. So they're tiny, but there's a huge range of sizes that fog droplets can be. And excuse me one moment, please. Please be quiet. Okay, I'm going to talk a little bit louder, I was told. See if I can raise my microphone level a bit, if you bear with me a moment. So I'll do the best I can to speak more loudly. Okay, hopefully you can hear me as I speak more loudly. This is a little slide here that shows fog droplets near corresponding rain droplets that are much larger than the fog droplets. So it gives you a kind of a perspective of how much larger the rain droplets are compared to fog. And that's significant because tiny little droplets like that tend to remain suspended in the air. Because of air resistance, they don't fall very quickly. Whereas rain droplets are going to fall at perhaps 1 to 2 meters per second. You can feel them. The bigger droplets, actually, you might have noticed if you've ever been in a rainstorm with larger droplets, they might actually sting a little bit because they're so much larger, they fall faster. Well, fog is so small, it falls so slowly, we're talking maybe millimeters per second, that it effectively remains suspended. And I already mentioned this, the droplet sizes are key in terms of the characteristics of the fog, the droplet sizes and the numbers of them. And that fog, again, is not a vapor. Now, given this, there's actually a bunch of different types of fog. One is called advective fog, and that's fog that blows in from the ocean where it's formed. And so this is the type of fog that occurs typically on coastlines. California coastline is a good example of that. It blows in from the ocean and tends to intensify over the land. Over the ocean, it's actually, while it may hinder visibility, it's difficult to collect water from it typically over the ocean than it is over the land. That's been our experience. And then as it rises on the land, let's say there's some topography, some hills, cliffs, near the coastline where the fog's coming in from the ocean. As the fog rises, it condenses even more. The vapor condenses more into the droplets. They become larger, and the fog gets thicker as you get higher up. So that's called an orographic effect, or you can actually have orographic fog, typically fog on the tops of mountains. Those kind of clouds you see on the tops of mountains, that's an orographic phenomenon, which happens because as the air masses rise higher over mountains, the air actually the liquid gets squeezed out of the air, and the droplets, and then accumulates more in the droplets. So the droplets can get thicker, and you can have more water, typically at higher elevations, and we've observed that as well. Now, there's other types of fog. I circled the two that are going to be the ones that I'm most interested in, because those are the ones that I'm able to collect the most water from and learn the most from. But there's other types of fog as well. Primarily, I'll mention the radiation fog, the Thule fog that some of you might be familiar with, that happens in California's Central Valley, for instance, is a type of fog called radiation fog, which is associated with the temperature difference between the ground and the air above it. That creates the temperature difference. Fog relies on a temperature difference to be created. And in the case of advective fog, it's typically a cooler ocean, warmer air. And for radiation fog, the air above the ground cools more quickly because the air radiates energy into basically space. It happens when the sky above it is clear. And that creates these tiny little droplets of water that accumulate on particles that are near the ground. And that's called radiation fog. And radiation fog is fairly static. You don't have a lot of wind associated with it. Whereas with advective fog, it tends to have a little higher wind going on with it. Radiation fog often occurs in still conditions. So that's another type of fog. And then there's others that I'm not going to talk about so much. But typically, whenever you get fog, you have to have a temperature difference in order to create the fog. And you have to have particles that the droplets can actually form on. And you have to have water vapor, perhaps a water source like the ocean that's allowing water vapor to exist in the air masses, so that when the warmer one cools down, that vapor can then condense upon the particles, creating fog. So of importance is, can we predict when fog will occur? And of course, the devil is in the details, as you might imagine. People often ask me, do you know if it's going to be foggy at a certain place at a certain time? Meteorologists can do some predictions, and they can tell you when fog, they will often say it's patchy fog, but they won't know exactly when it's going to occur. They don't know exactly where it's going to occur. My experience, though, is that's fairly persistent. In the places where it tends to occur more, it's going to occur more likely. But I can't tell you exactly when, but I can tell you some of the places it'll be more likely to occur based on measurements that I collect and have seen over the years from my experience. But it's very tricky to actually get accurate predictions of fog, and that's actually affected things historically, whether it's battles and things like that, where fog has just occurred and changed the course of what might have been a very decisive victory from one side fighting another side, because they couldn't see where they were shooting or whatever that was to try to win the war. The fog actually, there's some cases in World War II where that actually took place. So as I mentioned a few minutes ago, fog relies on little particles in the air to collect, or there's another term for condensation. It's actually a little bit more nuanced, called deliquescence. That's where tiny little molecules of water start to get attracted to little particles in the air, creating the fog. And eventually you get what's sort of an equilibrium where you get the fog stays fairly constant for a little while. But I'd say fog is in a constant state of flux. You have droplets forming, you have droplets evaporating. The equilibrium is when they're kind of staying in sort of a fairly consistent for a little while. But that, in my experience, doesn't occur much of the time. There's usually something changing, causing the droplets to either increase or decrease over time. So now I'd like to say a little bit about why fog is important, now that you know a little bit more about fog perhaps than you did a few minutes ago. Here's one example, or two examples actually, both in Chile. On the left, you see vegetation in a well-known international park in Chile called Fray Jorge. It's a national park in Chile, but is internationally recognized. And this park is in a semi-arid portion of Chile, meaning it's fairly dry there. It doesn't get a lot of rain a year, but it does get some. But most of the foliage that you see there obtains its moisture from fog. And so what you get in this region is you get patches of maybe a portion of an acre of foliage that exists, and then you'll have a drier area outside of it. And then you get another patch that exists where the fog happens to occur and the plants happen to absorb it. And that provides them the primary source of water for them. And there's trees here at Fray Jorge Park. One is called the olivio tree, which is actually not native to that area, but is found about 900 kilometers south off an island that tends to get much more moisture than this area does. So the fog actually has a huge ecosystem implication in terms of what plants and animals can survive there. On the right is a very arid location in the Atacama Desert, considered to be one of the driest regions in the world. And those plant-like structures that you see on the left side of the image on the right are called tillandsia, which a version of that are the air plants that some of you may know of that obtain their water pretty much solely from fog. They don't actually have a root structure. All of the water they get is from fog. So ironically, while this desert is the driest place on Earth because it doesn't get any rain, very rare that it gets rain, it does get a fair bit of fog. And that fog is what supplies those ecosystems that have the capability to capture those little droplets of water. Fog, and this is one of those pictures I've seen in a number of different publications. I just love it. These are, perhaps you may have seen them before, wind turbines out on the ocean. And what's interesting is, as a result of the wind turbines and the mixing that they're providing to the different types of air masses, they're actually generating fog downstream of them. And I've seen a number of different photos that illustrate this. But the photo's kind of a pretty photo, but it gives me it gives us the impression that fog is somehow tied to climate change. And it is. It's both affected by climate change in ways that we're still trying to understand. And it also affects climate change in the sense that fog is related to clouds, which clouds are a huge impact, or can have a huge impact on the impacts of climate change regionally and worldwide in terms of how much energy they're reflecting back into space. So fog is a part of that equation and part of that story, and something that's important to consider as we're looking at the impacts of climate change. And this is a little bit dated, but this is from a presentation I gave with Alicia Torregrosa, who I think is probably in the audience today, and others, that addresses some of the importance of fog. I think this is from 2014 or something like that. And it shows water usage in the state of California. And you can see that as you get further from the coast, typically water usage goes up because it's drier and hotter. So I won't say that it's the fog itself that reduces our water usage, although it can be, but it's often the environmental conditions associated with the formation of fog. Typically, fog requires cooler air, and that cooler air is going to result in less water usage. It's also going to form the fog. fog can also perhaps offset water use because it, as I mentioned, it's liquid water essentially. And so it reduces the evapotranspiration that plants perform. So it reduces their draw on the water. It reduces the dryness that happens that we often encounter with irrigation. So there's a number of ways that fog can actually impact our water use beyond just collecting water from the fog, although that is certainly one aspect that I'll also talk about. Then there's the direct human consumption. This is from a 1982, I think it was in Peru, a Peruvian newspaper. And what they're saying is, are we beginning to appreciate the fog? These are folks who are getting water from the fog. That's the idea here. And this is an example of somewhere in the Middle East. I don't know which country this is. It may be Morocco, where there are fog catchers set up to collect water from the fog that can then be used. So there's a number of places around the world where this is being done. It's not being done so much in the US. We can talk about why. But the needs have to be modest enough that the water you can collect from fog could provide the necessary water for human consumption. So this is one example of that. And these, I would say, are medium-sized fog collectors. There's much larger ones. And the ones I deploy are typically much smaller than this too. Fog can be used for agriculture. It can be used to provide moisture to whether it's gardens, or on the right, we actually see a field of aloe vera this is also semi-arid Chile. That's they're watering with fog water that they collect from up on the mountains, where you have that orographic effect that I mentioned earlier that enhances the amount of fog water that can be collected. And then the water is piped down and then provided and trickled into the aloe vera plants here. And I'll talk a little bit more about that one in just a moment. On the left, it's just a fog garden. So there's plenty of places, I know in Chile, where they're using fog for different irrigation purposes. In one case, watering an olive farm. I know also along the California coast, the presence of fog can actually perhaps allow us to moderate how much irrigation we provide to different plants, for instance, strawberries. So fog can actually, without even providing water, because as I mentioned, it reduces evapotranspiration, it may allow us to reduce the amount of water we use on some of the crops that typically consume significant amounts of water. And on the right, you actually see strawberries grown with fog water. I ate all of those. I shared them, of course, but that was in the Atacama Desert, where they're experimenting with agriculture in a greenhouse situation. And on the left, you can see lettuce that's being grown using fog water in the same greenhouse where they grew the strawberries. And then the slide I showed you a few moments ago, where we were looking at aloe vera and providing moisture for the aloe vera to grow. This gentleman here is part of a group in central Chile that's trying to grow fish, freshwater fish with fog water, and then using the effluent, the used water from the fish, which now has more nutrients in it, to provide water for the aloe vera and for other agricultural purposes. So not only are you watering plants that need the water, but you're providing some fertilizer for them too, and you're getting the fish as well. And as you can imagine, it's a big balancing act to be able to do that. And they're working with several universities to try to make this happen in a way that's potentially scalable. Fog water can also potentially be used for reforestation. And this is an example of in Spain, where they had wildfires a few decades ago. Of course, they have wildfires now throughout Europe. It's a huge issue. It's becoming an even bigger issue with climate change. But when there's wildfires, of course, there's reduced foliage to actually capture the fog water. Trees are excellent fog water capturing devices. Without the trees, you will not be able to provide the water for continued growth of the forest. So the idea is to put up quote unquote artificial trees, or these large nets throughout the area that you're trying to reforest, that can provide water to the seedling trees until they're able to take over with greater fog collection. As they grow taller, they have a greater likelihood of capturing more of these little droplets. Closer to the ground, there aren't as many of them available, but as you get higher up, there's more of them. And then there's a picture of myself and two of my colleagues in Chile at a restaurant, and the cups that we're drinking from are labeled Atrapa Niebla. And Atrapa Niebla is a type of beer that's sold in pretty much every establishment in this city in central Chile. And Atrapa Niebla means fog catcher beer, essentially. So it's beer made from water captured from fog. So they're actually making a fairly lucrative business out of it. And it was quite good. It was quite good beer. I enjoyed it. Very tasty. But it also has the added feature of being made out of fog, which gives it added attention. So how do I measure fog water? And I'm going to move now from the purpose of fog, or why fog is important to us and to the ecosystems in general, to talking a little bit more about measurements of fog and how I do that. And on the left, you can actually see a fog collector that I had deployed in Big Sur several years ago at Big Creek Reserve, which is owned by the UC system. And on the right, you can see a similar fog collector deployed in central northern Chile, outside of a city called Antofagasta. And this is actually the first site where they ever deployed these types of fog collectors in the 1960s. And you can see underneath why perhaps it is such a good site. The amount of water that this fog collector brings in each day is enough to supply this volunteer garden that happened underneath it. That was not planted. All of those plants there came and as a result of seeds and are thriving right underneath the fog collector. You can actually see how moist the soil is underneath it. This fog catcher on the right collects on the average of about 25 liters of water a day. And for those of you who are not as comfortable with liters as a unit of volume, that's about 6 gallons of water on the average per day. The one on the left at Big Sur collected nothing near that, but it was one of the sites I used. So I have 2 examples there, but I have many examples of different sites where these are deployed throughout both Chile and California. And on our campus at California State University, Monterey Bay, one of the sites we have a number of fog collectors deployed there, and it's been a great site for me to be able to test things and kind of in my own backyard, change things, change setups, work with students so that they can access them and set up different things. Right now, this is not the setup that's there exactly. We have a different setup, but this setup here had 5 different fog collectors, all located near each other, that were collecting fog and measuring they're using slightly different types of mesh so that we can compare how one mesh collected water compared to another type of mesh. This is also in the Atacama Desert, and this is a larger fog collector. These are probably about 20 square meters in size. There's a selfie of me near them, and you can see on the photo on the left, water dripping down. Well, you don't see the water dripping down, but you see the water storage system located below the large fog collectors on the hill there, storing the water that is then brought down and then used by the research facility here in the desert region of Chile. And again, I showed this picture earlier. This is another shot of the fog collector outside of Antofagasta and the volunteer plants that are happily growing underneath of it. Now I want to say a little bit about the grant that I'm working on with several colleagues, and I'm not going to talk about their research so much right now. I'll talk more about mine, but I'll mention what they're doing. We've been working on this grant now for a year. It's a 5-year grant. We're 1 year in. And our goal is to basically to understand fog and low clouds better than we do. And fog and low clouds, as I mentioned, fog is a cloud. Sometimes it's difficult to discern fog from low clouds from satellite imagery, and we'd like to be able to do that better. And also, how can we better make use of the fog and understand its impacts on the ecosystem and how it's changing as a result of climate change? and also look at how we can better model fog so we can better predict when and where it's going to happen and what its impacts are going to be on ecosystems. So we have a bunch of different research questions we're looking at. I'm not going to read them in detail, but these are some of the things we can think about. Fog water availability, what affects the efficiency of fog water capture? How do we capture more fog water than we currently do? How is fog changing? What are the impacts on ecosystems, and how does it affect the balance of different things that we're interested in, such as CO2 and water, and how they're both entering and leaving the ecosystem? And also, finally, I haven't mentioned this yet, some of my colleagues are also looking at the chemical and biological constituents of fog. What is in fog water? And is that something we should be concerned about? Does fog transfer things from one place to another that we may not want, whether it's pollutants or pesticides or things like that? And of course, as I mentioned, how can we better predict fog, both on seasonal and regional basis, and even on a much larger scale, decadal time scales. Let's say coast-wide times, spatial scales. So, hundreds of kilometers. How is fog going to change? Down to even on the scale of a kilometer or so. So fog exists at multiple scales, from the micro, even at the droplet size, which we're talking microns, to hundreds of kilometers, where it can actually cover coastlines or not. So fog has a huge variability in scale, and that's something we're very interested in. So this is the team of 5 researchers, that at least the primary investigators at each of the 5 universities, and I'll mention the universities. I'm on the lower right, California State University, Monterey Bay. We also have UC Santa Cruz. That was one of my colleagues, Peter Weiss, works there, and he's the chemical and biological fog scientist. San Francisco State University, Sarah Fogust is working there, and she's an ecologist, and she's also working with another colleague, Andrew Oliphant, who's a micrometeorologist, looking at the ecological impacts of fog primarily. And then on the right, Scripps Institute of Oceanography, Rachel Klemesha is looking at satellite imagery and modeling to better understand and predict fog. And she's working closely with Travis O'Brien, who's another fog modeler who actually got his PhD at UC Santa Cruz and now works at Indiana University. So he's the only out-of-state researcher on this grant, or I should say that Indiana University is the only out-of-state university on this grant. And he's also a modeler. So he's actually coming up and using state-of-the-art fog models to try to really better predict fog on multiple scales. Here's pictures of all of us and a summary of some of what we're working on here. And if any of you are interested, we have a website for this grant. It's Pacific Coast Fog Research, PCFR. So if you do a search and say PCFR fog, you'll find us online. And the Heising-Simons Foundation, if I hadn't mentioned that, is our funder. And this is kind of a reiteration of some of what I talked about earlier about looking at different work involving modeling and ecosystems and chemical and biological constituency of fog. My big focus happens to be on making measurements of fog water collection, which are used by all of my colleagues. So that's the aspect of the project that I'm most centrally involved with. So some of what I'm interested in is looking at things called fog water fluxes. Now, what does that mean? It basically means how much water and fog is passing through a given area, a vertical area. That's called a fog water flux. And I can measure that by collecting how much water is collected by the device that I showed you earlier, the standard fog collector, which you can see on the right. We're interested in how that affects the ecosystem and the surface climate of the area we're looking at. So I've been involved with deploying many of these devices throughout the state, and I'll show you a little bit about that in a minute. Actually, on this slide, I'll show you a little bit about that. So these are the fog collection sites that have been deployed just this past spring. I can say that my colleagues and myself have been very busy on the deployment um, front this spring. We're located somewhere here around where this green dot is. Up here, this is Fort Bragg, California. And so these are our northernmost sites right now. And this is about a 5.5, 6 hour drive, of course, depending on traffic, from Monterey up to here. So I've made a few trips up there with some of my colleagues from both my university and San Francisco State, where we've done a bunch of deployments up here that I'll talk about in a minute. And this all the way down here is La Jolla, which is an 8 hour drive for us. So we've deployed all the way down here. Actually, these have yet to be deployed. These are in the future. So right now we're really heavily focused on Northern California, and we have one site in Southern California. Next year, we're hoping to deploy here. But we've deployed pretty much at all but a couple of the sites in Southern California that we intend to deploy at. And we'll have some flexibility in the future as far as where we see gaps, where we want to put more fog collectors in. So as I mentioned, this is where we've currently deployed, but most of them are on the previous slide. But the names of the sites are listed here. And this is Mount Soledad down in La Jolla, near San Diego. And the rest of them are all in Northern California. And this is just from year one. So I think this year we deployed 13 different sites, and we deployed a total of 27 fog collectors, which adds to them, I would say, probably hundreds we've deployed over the past 15 years. So, but these are the ones that we're most actively looking at right now. And what's interesting about these deployments is that they cover a wide range of different ecosystem types, whether it's a redwood forest, for instance, up here in Fort Bragg, whether it's kind of a grassland, low-lying vegetation, which would be examples here at Bodega Marine Lab and Pepperwood Preserve, which have actually been deployed in the past, but also at Point Reyes. We have two sites in the Point Reyes region, a coastal site and a site that's a little bit more inland, both of which are more representative of this type of ecosystem. We have an urban ecosystem, San Francisco State, where there's a fog collector deployed on top of the building there. We have kind of a scrub oak ecosystem in the Fort Ord area, where we have several fog collectors that have been deployed. And then we also have some kind of deployed in more of an agricultural area in Salinas. So we have a wide range of different types of environments where we're looking at how much fog we're getting at different places. And the group that I mentioned that's primarily involved with the deployments on the PI scale, myself on the left and Sarah and Andrew on the right. And I also say that some of my students and former students are watching right now, and they've been very active in the deployments and very helpful both in fabrication and deploying. So I appreciate your efforts, and I appreciate you, and I know you're listening, so thank you. And this is, as I mentioned, is a basic station. Not only do we have a fog collector, as you can see here, but we have a bunch of different environmental sensors. These are meteorological. This is basically a meteorological station right here that measures wind speed, wind direction, relative humidity. We're also measuring rain in addition to fog, because you can have rain when you don't have fog, and fog when you don't have rain. We want to know when we're getting both of them. We're also measuring something called solar irradiance, how much solar radiation is hitting the region. And some of our sites also are looking at not only the light directly coming from the sun, but the long wave irradiance that the fog emits and that the ground also emits, both coming down and going up. We're also looking in some cases at soil moisture and also something called leaf wetness. So we have so many different sensors we're using to try to get a better understanding of all of the factors that can both influence fog and that fog influences. And this is a picture on the right of the coastal oak scrub, which is actually just a couple miles away from my campus at the Fort Ord Natural Reserve, which is owned by the UC system. And this is one of our primary sites for fog collection. Although we have so many sites right now, I'd say all of our sites are pretty primary, and a lot of effort has gone into the deployments this year of them. One of the things I'm particularly interested in is how to make the data available for anybody to access, including those of you who are listening. Often people want fog data, they don't know how to get it. There's a database that's being run by the UC system called Dendra. And one of our goals is to get all of these fog collectors and their associated ancillary environmental data products into this database so that anybody can access them. And that'll also make it easier for us. One of the challenges, if any of you who are listening have worked with environmental data before, is the fact that you get all these different files that have different formats within them. And the data are listed in different ways, which makes it really difficult to make it generally useful. And even amongst researchers, we have to supply all this information, and it's not done in a standard fashion. And that's what we're hoping that this database will allow us to do, to really facilitate the use of the data that we're collecting from all of these sites. One of the other things I'm involved with on this project is to actually measure the tiny little droplets of fog, as I talked about earlier. How many of these droplets do we have within a given volume of air, and what are their associated sizes? You got big ones, you got little ones. These devices are called optical spectrometers, and they're constantly measuring the number and size of the droplets within air masses. And I like to just turn them on when fog is available, but they typically run 24/7. And you can see when a fog event comes through because they show you droplets, and they show you how those droplets vary over time. And it's fascinating because, as I mentioned earlier, they come and they go. So fog is almost kind of a living thing. It's kind of breathing in and breathing out. It comes and the droplets change in size and numbers, and then 10, 15 minutes later, they can change dramatically. So it's a very dynamic phenomenon. And these are the type of data here. You can see that these are the droplet sizes that are listed down below here. And the size of the bar here represents the relative number of droplets within each of these bins. But I call this almost a fingerprint of the fog. These change over time. And the smallest droplets are on the left, the largest ones are on the right. And when you have larger droplets, you're more likely to have more water in the fog, because larger droplets hold a lot more water than smaller droplets. And so one of the projects I was involved in, this is during COVID, was to actually set up these droplet measurement devices in conjunction with the standard fog collectors. So I have one in front, one behind. And using that, I can actually get measurements of how effective my fog catchers are in extracting water from fog. And I have some photos of some of our recent deployments. This is one at a Long Marine Lab in Santa Cruz. It was our first deployment this year in April. This is a deployment this is actually a movie. I'm going to show you this. This is a fog catcher that's being lifted up a tower in a redwood forest. And this is one of two towers where we have fog catchers deployed on. And you can see that. And we're actually physically lifting this up this side of the tower. It's kind of fun to see that. And you might ask, how high did it go? I'll talk about that in just a moment. So this tower is one called Parlin Tower, and it's one of two towers in a redwood demonstration forest that's set up to better understand the environmental conditions underneath the canopy of the redwood trees. And this is the first time, as far as I know, that anything like this has been done where we're actually measuring how much fog water you can collect at different heights within the canopy of a redwood forest. So this tower actually has two different fog collectors on it. One I think is probably at about 30 meters. The other one's at about 6 meters. But we have another tower called Mitchell Tower, where we actually have 4 of these fog collectors deployed at different heights on the tower. I don't have a photo of that in this presentation, but I have some data from that. And it's fascinating that the highest one is about 47 meters up, which is about 160 feet up. And no, I was not allowed to climb the tower. These are the folks who run the tower who had to do all that. But I was at the bottom with some of my colleagues providing support so that they could get our fog collectors up to the top. And they're collecting fog water every 5 minutes when there's fog and nothing when there's no fog. But I'm getting data in pretty much real time from one of these towers. at 4 different heights: 47 meters, 30 meters, 20 meters, and about 6 meters. And we're seeing some fascinating patterns of where the fog exists within a redwood forest at different heights. And yeah, this is these are two of the fog collectors at Parlin Tower, and it's quite a ways up. This was a close-up photo. You can see this one's near the canopy top. This one's a little bit below. And then this is the fog collector at in La Jolla. And these are two of my. This is Jason on the left, one of my former students who's now working with me, and one of my current students, Ryan, is on the right. We were very happy after we deployed our southernmost fog collector there in La Jolla. And fog, of course, gets a lot of press. This is a recent Mercury News article about our fog project and how we're better hoping to understand fog. And this is some information from the website on the Heising-Simons project. But I'd like to show you a little bit of data here. I mentioned one of the towers. This is, we deployed 4 fog collectors at a tower called Mitchell Tower in near Fort Bragg. It's one of the ones I mentioned. We were at 4 different heights. These are the 4 heights I mentioned. The blue represents the highest fog collector in the tower. It's a 47-meter height. And you can see we had a pretty good fog event. This is when we deployed it on the 15th. Even on the 16th, we got our first event, I was real excited to see that. But on the 17th, and the fogs are, of course, occurring kind of in the middle of the night. That's when we're seeing it. And these are daily totals. So this represents the daily total of all the fog collected from each of the fog collectors at each of the heights. So on the 17th, between the 17th and the 18th, I think this is the 17th here, at the 47-meter height, we got about 1 liter of water. And at the lower heights, of course, we collected smaller amounts of water. You can barely see them. But that's to be expected, that within the canopy, the redwood actually scavenges most of the fog water. So as you get lower in the canopy, you collect less fog water. And there's actually there's research on how much less you should see, and the amounts we're seeing are mirroring that research. So we're in the expected range of what we would think we'd see. And of course, on these other dates, you can see we had some very significant events. The most significant occurred on June 24th here. And this was interesting to me. On June 26th, we saw fairly significant fog water relatively at the lower heights here. And I actually looked, and this was because of rain. So this is something I'll actually filter out later. This was a rain signature, the only rain that we had during this time period. Typically, you don't have as much water in the lower within the canopy as you've got on this date. So I was curious about that. That was because of rain. But we can see the different amounts that we're seeing at different heights within the redwood canopy. And if this was from June 15th to just a few weeks ago, July 21st or so. And then you might say, well, what about looking at it more frequently? Well, here's what I did. I took these data here between the 24th and the 27th, and I blew them up so I can look at data collected hourly. So with the ability to do that, I have the ability to look at data on a very fine scale of every half hour. In this case, I'm looking at data every hour. And we can see that we had a big fog event here, but we can see when it started. It started around midnight on the 24th, and it went until the early morning hours of the 24th. This is noon. And you expect that you're not going to see much fog during the day when the sun burns it off. And then in the late afternoon, early evening, it comes back and then burns away. And you see that at pretty much any of the fog collection sites I have. And here's the rain that I mentioned earlier. The signature here is because of a rain, as well as perhaps some fog that gets mixed into it. These are data from 3 different sites that I thought I'd show you. The green one is the photo I showed you, the very first photo I showed you a few minutes ago of myself and my colleague Sarah at Long Marine Lab. And these are the data from the green Long Marine Lab Santa Cruz fog collector in green. You may say, well, that's not very much. What's going on here? And that's true. And the orange data are from one of our sites in Point Reyes State Park. These are the data that are from that fog collector. We get significantly more from that fog collector. And the data from Mitchell Tower that I just showed you are shown here. You may say, how come you don't have any data from Mitchell Tower here? And the reason is because we didn't deploy it until June 15th, 16th, which is right here. So there probably were fog events here. We just don't have them. So we're seeing the daily totals from 3 different sites right here. So these are the kind of things we can look at. What's interesting is you're not seeing necessarily coincident fog events. Sometimes they are, like you could say perhaps these are on the same day, but there were events happening on Mitchell Tower that weren't happening at Point Reyes and vice versa. So you see some fog events were very regional. Others were perhaps larger in scale, or we call that synoptic, maybe driven by larger forces. So you can see evidence in this data set of when we do and don't have fog. And one of the things you do notice also is that when you don't have fog, you often don't have fog in a bunch of different areas. But sometimes you can not have fog in one area, but you can have it in another. So these are interesting new results. And this is the last data slide I'm going to show you. And this represents fog from, I will call it my most productive site. And that's one of my sites near Pacifica at the North Coast County Water District, where they've been very generous in allowing me to set up a fog collector for several years. I have data from this year as well. I'm not showing that yet. But these are data. These are monthly totals of fog water collected from 3 fog collectors that were located within 100 meters of each other at the North Coast County Water District in Pacifica. And you may say, why are there 3 different colors here? Well, because I have 3 different fog collectors. The green one is the one that's most productive. That's the main fog collector I have. And it's always the most productive one at that site. I've never had it produce less than any of the other ones. And the red one is one of the other sites at there. And then the blue one is the 3rd site. And you can see that sometimes they trade off. Sometimes the red ones produce more than the blue one and vice versa, which is interesting, at least in 2024. In 2025, the red one always outproduced the blue one. But the other thing that's interesting is if you look at the total amounts of water produced on a monthly basis, it always peaks in August, pretty much from all of the sites. So you can kind of see, this is the fog season. It begins in May, peaks in August, and then goes back down in October. It goes back down to a much lower amount. We do get fog year round, but it's much lower. But the peak amounts, this is from 1 square meter. We're getting 250 liters of water in a month during the month of August from this most productive site. We're talking 8 liters of water or 2 gallons of water a day from a square meter at this site, which is 10 times more than we're getting at almost any other site. So it's a fascinating site, and I'm really thrilled that we have the opportunity to collect fog water from there. And I want to end here and allow time for questions. I can go into more depth, and I can show you some of the other data or other things we're talking about. But I'd rather give you a chance to ask any questions that you might have. But I want to thank you for your attention, and go back to Zoom here.
Professor Fernandez, thank you so much for that presentation. So much information and so many things that I never would have expected. Growing up in the Bay Area, fog is, just another thing that rolls around every year. But to learn about ocean wind turbines that are generating fog in parts of the world, fog water beer is something I never thought I'd ever hear of. We do have lots of questions, and I want to be mindful of everyone's time. But before we get into them, can you speak briefly about some local habitats that benefit from the fog and perhaps source most of the water they need from the fog?
Certainly. Most common one that is talked about is the redwood environment, where I showed you those photos of the data that we have, the photo of the towers, and also the graphs of the data that we have at the different heights in the redwood forest. And redwoods, coastal redwoods, take up about 40% of their water from fog. So that is one very significant ecosystem regime that's very fog dependent. But even the coastal scrub, that oak scrub that is from around here, gets a significant amount of water from fog. There's types of manzanita and other, I'm not a plant person, but I know there are certain species of manzanita that are fog dependent, for instance. And there's other types of lizards that are dependent both upon the moisture and the temperature associated with the cooler regions that are fog emphasized that that utilize that ecosystem that are dependent upon the fog in that regard.
Wow, lizards as well. Okay, let me get into some of these questions that are in the chat. I'll go in order in which they were typed in. How does ocean warming affect coastal fog?
That's a great question. I would expect that if we do have ocean warming close to the coast, that you're going to probably see less fog as a result of ocean warming. And that's one of the questions that comes up with what's climate change going to do to fog. Because climate change in the short term may actually, in some cases, enhance upwelling, which could result in cooler areas at some locations, which may enhance fog. But in other places, as the ocean gets warmer, generally warmer, you may get fewer upwelling regions happening. So there's kind of a push-pull happening there with climate change, making it difficult for climate modelers to fully give us a picture of how climate change is going to impact fog. But if the ocean were to just generally get warmer, you're going to have less fog in those regions.
Okay. Next question. Do the collection devices, artificial trees, work for just fog, or can it work for general humidity? Like, could I put one in my yard in Santa Clara Valley and water my plants?
No. I'll be honest. And I appreciate that question because I know a lot of people are like, hey, I've had calls from the Midwest all over the place. Hey, can I set up a fog collector in my house we're having water issues? And it's like, don't waste your time. Don't waste your money. No, you have to have fog. It's got to be in liquid form. Now, there are other technologies that can extract water from humidity, but they're active. They require energy typically, although there are some technologies that are being explored that I know a recent Nobel Prize at UC Berkeley is looking at devices that are passive that pull water out of the air, but I don't think they've actually managed to scale it to get large amounts of water coming out of the air. But that would be great if we could. But in order to get water out of humidity, you really, in order to make it work, you need energy. And that's an active system. And there are devices that do that actively pull, they're basically dehumidifiers, but I would say deluxe dehumidifiers would be a way to put it. And you can get drinking water out of them.
Okay. And what sort of material are these fog collectors that you showed made from?
The ones that I use, I've used several different types of materials, but the standard material that I use is called a Rochelle, which is a type of mesh that's interwoven. So if it gets cut, it won't unravel. And I use a double layer of a 35%, it's called a shade coefficient. That means if you shine light through it, 35% of it will be blocked by the Rochelle mesh. So if you use a double layer of that Rochelle mesh, somewhere between 50 and 70% or 50 and 65% of the light is blocked. And that proves to be close to, I don't know exactly what optimal is, but a double layer does better than a single layer and does worse than a triple layer. I've also used 50% shade coefficient Rochelle mesh and seen similar results as a double layer 35%. So it's a mesh that's about a millimeter wide, and it's kind of a fine fiber that collect the fog water. And then there's also a German mesh that I really like as well. That's more of a thread-like material that is kind of a three-dimensional structure that looks like a bunch of hexagons. It kind of reminds me of a beehive. And those little fibers are actually really good at collecting the water too. They collect, a similar amount to the Rochelle mesh, maybe 5 to 10% more, but measuring those smaller differences, there's a lot of things that can affect the measurement. But I would say they may have a slightly higher efficiency than the double layer Rochelle mesh, but not particularly significant, maybe 10% more.
Okay. Next question. Is there data on how much water can be collected per year in one of your setups?
Sure. I mean, I have data from many years, and it depends on the site. It's really site dependent. And one of the things I'll say, some of my students and colleagues are working on this along with me, is even if you have fog collectors all within a given region, like when I region, like a given acre or two of land, and at the CSUMB campus here behind our library, I have 13 fog collectors set up that have been up there for about 8 years. They're actually larger than the standard one, and they're watering oak trees, sapling oak trees, which has been real exciting. But I'm also collecting data from them. Even fog collectors that are just 15, 20 meters apart can collect, one can have 30, 40% more water than the other as a result of local wind patterns, we believe, that are driving how the fog moves around these devices. So yes, I can give you numbers, but those numbers are not necessarily representative of a general area, but of that specific site, if that makes sense. There's a lot of variability, is my point.
Okay, yeah, we have another number question here. Are there any trends refog from year to year? And how has this summer's fog been typical, more or less?
I didn't catch the first part of the question. Any
Sure.
trends?
Are there
Yeah.
any trends in fog? It says, are there any trends refog from year to
Oh,
year?
regarding fog, got it. Okay.
Yes.
Um, there have been some trend, not clean trends. So I haven't seen this. I haven't seen this. So it's not like, oh, it's all getting less. It's all getting more. I would say it depends on where you're measuring it. Some places are seeing more. Some places are seeing less. I would say in general, this has not been a great year for the locations that are lower. We've seen fewer fog events. Long Marine Lab's a great example. You could barely see any data on that graph for this year. But at some of the higher elevations, Pacific is still getting a fair amount. It may be a little bit less than last year. I won't know till the end of maybe the end of August when it's the peak. And there's been other years where we've had less fog and then more fog. So I wouldn't say a trend. I'd say it's variability as a result of a number of factors. Climate change is probably overriding all of them, but I can't see that because I don't have long enough data set to see it. But even there, you're going to have, it's not a simple increasing or decreasing, which is satisfying. We're going to see an increase or decrease in fog. That I don't think the answer is as simple as that. It's a question of where and when you may see decreases and then increases for some of the reasons I talked about upwelling and ocean temperature. It's not a uniform increase. And then in general, it may be increasing, but there may be some years where we have more upwelling near the coast and you're going to get more fog. So I think that's the best I can answer that question, which is an excellent question.
Yeah. Our next question, do tell us more about the impact of the fog and its significance for the ecosystems, please.
I think I hit a little bit on that in the talk, but I'll try to go a little bit more. I mean, fog provides, I wouldn't say fog is what cools the area, but fog is associated with cooler temperatures. And fog will also provide more reflection of solar radiance. So as a result of the areas that tend to have fog, you're going to have, let's say, cooler water temperatures in rivers, which may support the survival of trout or different fish species. You'll also have cooler temperatures along the coastline, which makes it more survivable for species that are dependent upon the coolness of the foggy environment. As I mentioned earlier, the redwoods are fog dependent. That's an ecosystem that's dependent upon fog. So if there's reduced fog for extended periods of time, there may be adverse effects upon the foliage that depends upon it, which can include redwoods, but can also include other types of species, for instance, some pine species. There can also be other impacts. Fog can impact parasitic species, molds, fungi, mildew, things like that. And so if you have less fog, you may actually have fewer diseases on some plants. So it's not as simple like, oh, we need more fog in all places for all plants and all species. Fog can have different impacts on different plants and different animals, but those that depend on it can be adversely affected if it's going to decrease. So that's the kind of the best general answer I could give right now, I'd say.
Okay, thank you. I'm glad someone asked this question. Why is August such a foggy month on the coast?
It's a great question. I would say it's probably mostly because the conditions, I'm going to be real general here, a combination of the ocean temperature and the air temperature conditions provides enough of a temperature difference to drive the formation of fog and to bring it inland. So you continue to get more of the advective fog, which is going to be driven inland and then brought up if you have, as mentioned, that the increase in elevation, which Pacifica sees at least for 300 or 400 feet up, which isn't that much, but uh, it it's going to. I'd say it's because you have a larger number of days where you have those temperature differences, so the conditions are better for the formation of fog and for significant amounts of liquid within the fog.
Okay. Next question. Is it possible to convert the collection volume data to represent its production or across an area on the ground?
Yes, but it's difficult because you have to know. Uh, that's actually some of the earlier studies in fog water collection focused on doing that, trying to translate how much water here is going to translate to water on the ground. One of the mistakes people make, I would say, is collecting water from the mesh and then having that water in millimeters as if it's rainwater, and then saying, oh, we're getting 10 millimeters of water from fog. Wow, we're missing this huge amount of water that we don't realize is happening. That's not happening. That's what your mesh is getting, and that's what the bucket that you're beneath your mesh is collecting. But the only things that are going to be getting that much water are the things that are directly collecting it and dropping it below. And most places aren't doing that. Maybe in front of a certain tree you'll get that. Um, and so you need to know what I'd say the rugosity or the type of vegetation that exists there is picking up, so that we can have a model to convert the amount of and knowing the wind patterns, so we know how much of that liquid water that's in the fog is being collected upon the tree and then dripping down. So it requires another step to do that, but it's certainly doable, and there's models that can do it that depend upon the height of the tree and how much foliage there is and things like that.
Okay. And last question, is fog water potable for humans and animals?
I would suggest that if you're going to be drinking it, that you treat it as I would with rainwater. But fog water is going to have even more stuff in it than rainwater for a number of reasons. Each tiny little droplet of fog has a particle in it that the droplet formed around. Same with rain, but the rain's bigger. So rain probably has less stuff in it. Also, rain falls directly from the clouds to the ground. The transition time might be a minute or a couple minutes, and the time it takes the rain to fall from there to there, a few minutes. Fog lingers. It can linger in the air, and the droplets linger in the air, and the particles linger in the air. So they're going to be absorbing whatever chemicals and whatever things are in the air. So fog is going to tend to be an enhanced version of whatever's in rain is what you're going to find in fog. So you want to be careful and thoughtful in consuming water. For animals, that may be less of a deal, but it depends on what the animal is, what their sensitivities are. So certainly possible. I mean, they're out drinking from puddles. So in some cases, depending on what the animal is. So I'd say with animals, it's more likely they'd be able to consume it than with us.
Okay. That concludes the questions. There was one or two that was answered in the chat, perhaps by a colleague of yours, Professor Fernandez. So again, want to be mindful of everyone's time. Professor, thank you so much for generously sharing your time and expertise with us today. I know I got so much out of this. I'm sure so many folks here did, giving us a better understanding of our home and one of our local weather phenomena. Thank you to everyone who joined us. I hope you all appreciated and enjoyed today's talk. If so, perhaps consider making a donation or referring a friend to Bay Nature. And that is all for today, and I hope to connect with you all in the field at a future event. Thanks, everyone. Thank you so much, Professor Fernandez.
Pleasure. Bye-bye.
Bye-bye.